So welcome back at the deep mitigation session. I hope that Sergey will join us soon with the official share of this session. And so this morning we have looked at a lot of negative emissions and CDR. Before the break, we have looked at a lot of negative emissions CDR technologies. We will now see a lot of other strategies to go to deep mitigation. And the session starts off by a presentation by Oreane and EDELENBOSCH. So the floor is yours.
Thanks. Great. So good afternoon, everyone. My name is Oreane EDELENBOSCH. I work at Utrecht University. But this is actually a study that we've been doing with almost the whole image team. So partly at Utrecht University and PBL Netherlands Environmental Assessment Agency. And I listed a few people that were involved here, but the group is actually a lot bigger. So the study looks into deep mitigation pathways in the hard-to-abate sectors. So the short introduction, basically, if you're looking at net zero targets, then there are certain sectors, so the so-called hard-to-abate sectors, where residual emissions remain, and they're mostly buildings, industry, within transport, aviation, international shipping, and agriculture, non-CO2. And so these residual emissions make us more reliant on negative emissions actually to reach net zero targets or carbon dioxide removal technologies, but these also come, of course, with a cost. And in particularly the reliance on BECCS, so bioenergy and CCS, that is highly uncertain, and especially also the large scale that it's applied in many of our scenarios, and its requirement for land and water, raises the questions if this is feasible, and if also we could by decarbonizing these hard-to-abate sectors reduce our dependency on negative emissions. So that's really what this study is about. So we focus particularly on 4 domains. That is the aviation sector, the building sector, agriculture, non-CO2, and industry. And there are 2 main questions that we address. So first of all, within these domains, can we try to reach almost zero, or how low basically can we go? And secondly, what does that mean for the dependence on CDR technologies? And to be honest, we are still in the process, so we're still working on this project. So this presentation will mostly focus on the first question. The method that we did was, first of all, really do an in-depth literature review where we addressed 3 main questions. So what makes these sectors so hard to abate, and what are the key obstacles? And then which measures and policies can help to overcome these obstacles? And so this last question was then translated into a scenario matrix, where we focus for all the different hard-to-abate sectors, on one hand on technology changes, and on the other hand demand changes. And the reason for this is that we saw that in these hard-to-abate sectors are in particularly characterized by a strong growth in demand, so demand for the services that these hard-to-abate sectors provide. And on the other hand, they're not easy off-the-shelf technology fixes. So that's why we made this distinguishment. A second distinction that we made was between incremental changes and structural changes. And here with incremental, we mean changes that really fall in the way that the sector currently operates, while as structural changes would be fundamentally change the way of operation. So this was then implemented in image. Just a very brief overview or a brief introduction, because I'm sure that most of you are well aware of the image model. So basically, it's a process-oriented integrated assessment model. So it has mostly details on the physical world. So on the one hand, the energy details on the energy system and also on agriculture and land use, with, for example, details in transport and also sub-transport modes, industry subsectors, but also residential and services and different income groups, different household representations, and also including, for example, the age of buildings. On the agriculture side, there's quite a detailed economic modeling of trade and demand for agricultural products, as well as the modeling of land use cover on a gridded scale. The model runs from 1970 to 2100, and it's a simulation model, and the main drivers are demographic, economic, technological development, resource availability, lifestyle changes, and policy. And for this study, we based our analysis on a default or middle of the road SSP2 scenario and applied then a really rapidly rising carbon tax. As we kind of see it as our maximum or fastest changing carbon tax, so which would until 2025 follow NDCs, but then very fastly change to a general global carbon tax in 2035 of 1750 US dollars per ton CO2, and then in 2050, 4,000. And at the same time, we applied a limit on the available bioenergy of 60 exajoule based on a paper of Fuss et al. To also accommodate kind of the reduced reliance on bioenergy and really accommodate this shift. The scenario results were analyzed based on a decomposition method, where I guess this is also familiar for most of you, but the idea is that direct emissions in a sector can be decomposed to different changing elements. So on the one hand, population change, then activity per population, which could be something like in the transport sector, the passenger kilometers, or in the building sector, the floor space, then structural change, such as modal shift, and an efficiency component, which could be energy per activity or land use per activity, and then a kind of an emission intensity component. And then finally, we also looked at a kind of in top of this very high rising carbon tax, also a scenario where we apply the same scenario matrix, but then optimizing an optimized carbon tax pathway to remain within 1.5 degrees. So just briefly give you an overview of the results that we got from our literature research for the aviation sector, because it was how we build up also our scenarios. But of course, because of time constraints, I won't be able to go through all of the sectors. So the aviation sector, so what we did is basically characterize the hurdles on the one hand, and then the measures. So those are the kind of the changes that can take place. And then the policies, which are the levers that could enforce these measures, so these changes. So the aviation sector, for example, is characterized by, it is of course an international and a very highly competitive industry, but it also has a long lifetimes of infrastructure and as well as the technologies or the planes. Fuel is only a small share of the overall cost to travel, which also makes it less responsive to climate policies, and it's characterized by fast rising demand, and it's carbon and currently very carbon intensive. So different measures, so there are certain fuels that are available currently and can be implemented directly in current planes, such as power to liquids and biofuels. But there are also other measures, such as shifting to other forms of transport or reduction of demand due to alternative tourism or increased teleworking. And then there are measures that are more looking at the efficiency of the current aircrafts or in the current operations. And so these can all be different policies address also the different measures. So this was then translated to these four scenarios. So in this case for aviation, in demand incremental, smaller changes within the current way of operation, so applying a ticket tax, less demand for aviation trips. While as in the structural scenario, we implemented really a shift from short distance aviation to the use of high-speed train for those countries where currently high-speed train infrastructure is in place, and also a reduction on the demand due to teleworking and alternative tourism. Then for technology incremental, there was a shift towards more efficient planes and also the use of these drop-in fuels, while as the structural would really go beyond that and make use of electric planes for short distances and have a way faster market turnover also. So this is kind of how we build up the different scenario storylines for each domain. How much time do I still have? Because I have the feeling we started a bit later, but I also have the feeling I might have to skip a few slides.
Yeah, you might want to round up in about 2 minutes.
Okay. So in a similar way, we build up the scenarios for buildings, industry, and agriculture non-CO2. And this led then to these new pathways. These are the decomposition results for the passenger transport, in which you can see the roles of aviation. So basically the top left figure shows how the CO2 emissions would develop from 2015 to 2050 as a result of population activity, modal shift, efficiency, and then the intensity, carbon intensity. And so you can see that also so in the baseline, in our scenario, aviation plays or has a way larger share in emissions in 2050. And in the mitigation, so this is the standard mitigation scenario, and actually this compares emissions of the mitigation scenario in 2050 to the baseline emissions in 2050. So you can see the left column is the same as the right column at the top figure. And so what you see is that mostly reductions take place in the other modes. And although there's some improved efficiency and also some modal shift away from aviation, overall in 2050, the residual emissions are mostly coming from the aviation sector. So then if we look at our quadrant, the demand incremental changes results in, compared to our reference scenario, reduction in activity and also further modal shift away. And this actually has quite an impact, but an even higher impact, of course, in the demand structural sector, where emissions are almost half of the residual emissions in the reference mitigation scenario. The technology scenarios also show increased reduction mainly in the last two components. However, because especially electrification is mostly applied to short distances, overall the effects are less large than the effects that we see in the demand scenarios. Okay, I will skip through the industrial decomposition and then directly go to the overall results at the domain level. So what you can see here is then for each domain, the emission pathways in the SSP2 scenario compared to the demand incremental and demand structural, tech incremental and tech structural. And if we just focus on the demand structural and tech structural, so that's the orange line and the yellow line, you see actually that the demand structural in aviation, industry, and agriculture has the fastest impact on emissions. So it really allows for a fast reduction, while as the technology structural shows more deep reductions over the long term. And yeah, in all domains, it's clear that the structural scenarios have quite a significant impact on top of the already quite ambitious mitigation scenarios. And then very quickly, so in the optimized 1.5 degree pathway, so this is SSP2 compared to demand structural and tech structural, you do see, which you would expect, of course, also the quite high reduction of negative emissions in the electricity sector as a result of these measures. So that's the light blue. Well, because of time, just round up with the conclusions. First of all, so the hard-to-abate sectors, of course, will become more and more important in the future and taking up a larger share of the emissions. And what we found by this quite in-depth analysis of the different additional measures in the hard-to-abate sectors is that these structural scenarios do really have quite a large impact still on the residual emissions and would reduce the reliance also on negative emissions, in particular BECCS. And we see these different contributions that demand changes have compared to technological changes, where demand happen more in the short term, and while the additional technological changes would have deeper reductions in the long term.
Okay, thank you, Oreane. I would propose actually that if people have questions to Oreane, we first of all post them in the chat. It might be that by the end of the session there's still an open discussion, so we could return. But I think people could first post the questions in the chat, and Oreane can respond in the chat. I would like to go to the second presentation, which is on the socioeconomic pathways to meet Thailand's 2-degree target. I have a little challenge here, so I would announce the speaker first of all as Achiraya, and I would ask the speaker to.
Good evening from Thailand. My name is Achiraya CHAICHALOEMPREECHA. I am a PhD candidate from SRIT Thammasat University, Thailand. Today, I'm going to present possible shared socioeconomic pathway to meet Thailand 2-degree target. The presentation's outline can be divided into 4 parts as follows: introduction and analysis to result and discussion and conclusion. Climate change became a challenge issue worldwide. In 2015, IPCC earned the Paris Climate Conference, or COP21, which led to an international climate agreement called Paris Agreement. Paris Agreement is a legally binding framework between all nations to tackle climate change. The main objectives of Paris Agreement are limit the global temperature increase well below 2 degrees Celsius and pursuing effort to keep the temperature increase to 1.5 degrees Celsius compared to the pre-industrial level by 2100. Thailand announced its NDC, which intend to reduce the GHG emission by 20 to 25% from its BAU level in 2030. In 2021, in COP26, being all party together to accelerate action towards the goal of Paris Agreement. In order to achieve such goal, Thailand Prime Minister presented Thailand's intention in achieving carbon neutrality in 2050 and net zero GHG emission in or before 2065, and Thailand can accelerate its NDC target by achieving 40% GHG reduction in 2030. In order to achieve the 2-degree target, this study aims to analyze the potential effect of carbon price on energy and GHG emission in Thailand. The comparisons of no carbon price and carbon price pathway are determined. In addition, the mitigation timing and net zero emission are discussed in the energy sector by using Thailand MN-use model. This slide shows the concept of MN-use model. The MN-use model consists of 3 components, including energy, energy technology, and energy service. Energy technology are devices that provide useful energy service by consuming the energy. The energy information consists of fuel type and fuel price. It's also designated emission factor to determine the emission. The energy technology considers the detail of the technology, such as capital cost, energy efficiency, and ride time. The energy service refers to the demand within the individual sector. This study considers the carbon price in line with the SSP4 and the RCP 2.6 scenario to meet the 2-degree target. The scenarios are divided into 3 groups, namely business as usual or BAU, the carbon price without CCS or CT, and the carbon price with CCS or CT-CCS scenario. Several carbon prices are considered, including $0 per ton carbon dioxide and 4 different carbon price pathways obtained from the IAM under the SSP4 scenario in the RCP 2.6 as shown in the graph. This study considers the CO2 removal by forestry area. The Royal Forestry Department of Thailand announced that the total forest area will be increased to 40%. The Thailand Royal Forest Department project the economic forest area will increase to 15% of the country total area. This study assumes that the 15% increase will be in 2030. It was assumed that the area will constant toward 2050. Figures show the CO2 removal by sinks in this study. Total CO2 removal by sink will be 187 million tons carbon dioxide in 2050. After considering the CO2 removal by sinks, the net GHG emission in the BAU scenario will reach 800 million tons carbon dioxide equivalent in 2050. The GHG emission in the CT and CT-CCS scenario will significantly decrease by 33% to 59% and 44% to 74% compared to the BAU scenario in 2050. The immense CCS scenario will reduce the higher GHG emission about 74% compared to the BAU scenario. By imposing carbon price, the increase of solar, wind, and biomass electricity, power plant energy efficiency improvement, and energy saving will be a key option towards a clean power generation in the CT scenario. Pursuing the net zero CO2 emission in the power sector, the CT-CCS scenario assumes the CCS technology will be available. CCS will become a cost-competitive option for the power sector. Power sector will reduce the highest GHG emission. The GHG emission will reduce more than 50% in CT scenario compared to the BAU scenario. Due to the CCS technology, CO2 emission in power sector will reach 0 in the GCAM CCS, image CCS, and with CCS scenario. This slide shows the energy supply in power sector in 2050. In the BAU scenario, the electricity generation will dominate by natural gas power plant. It will account for 65% of total energy supply in 2050. Coal consumption will continue its use in T0, MC, and GCAM scenario. In the image and the risk scenario, there will be a substantial shift from coal-fired power plant to natural gas-fired power plant, biomass, wind, and solar in 2050. The coal consumption will continue to supply in the TCCS scenario. Such a consumption will supply to the power plant with CCS. This slide shows the electricity generation mix in 2050. Natural gas-fired power plant will be a main power plant in the BAU scenario. Renewable electricity will maintain its share of 7.2% from 2030 to 2050. Renewable electricity will play a major role in the CT scenario. The generation from renewable energy will increase to 60% in 2050. In the CTCCS scenario, the renewable electricity will account for 58 to 59% in 2050. Coal and gas-fired power plant with CCS will contribute over 200 terawatt-hours in 2050. And BECCS will also play an important role. In the conclusion, this study aims to analyze the potential effect of carbon price on energy and GHG emission to meet Thailand 2-degree target. The SSP-4 is considered as a situation that's consistent with current socioeconomic situation in Thailand. The related carbon price of RCP 2.6 are considered, and the CO2 sequestration by forestry is also considered. In 2050, the power sector will reach the net zero CO2 emission in the CTCCS scenario. Presently, the renewable electricity is cost-effective option in reducing the GHG emission. The CCS and BECCS will be a cost-effective option after 2030. And finally, I would like to thank National Institute of Environmental Study or NIST Japan for supporting the AIM model. And thank you for attention.
Thank you very much. I think, well, we are doing a teamwork with Detlef, so I'll continue here. So any questions? I don't see any questions in the chat so far. Any questions live from the audience? Okay, so I think we are catching up in terms of time. And we have some discussion time built up at the end of the session. So again, please use the chat option so that we will have a great discussion session at the end. Now let's go to the next speaker. So Camila de Oliveira, and Camila, if you please can start sharing your slides.
Sorry, Sergey. First announcement is that unfortunately Camila cannot present today. She had an unforeseen event. So I'm Pedro. I'll present her stead.
Okay, Pedro. Thank you very much. Thank you for stepping up.
So basically, that was my first announcement. Was that Camila is not the one making the presentation today, unfortunately. I'm using her slides that she sent to me. So I'll probably butcher a few of her lines, a few of things that she had planned during the presentation. I'll do my best to present her study. So we start by discussing the dilemma between bioenergy, which is the classical tale of bioenergy and food competition. And our proposal is to add one more leg to this dilemma, transforming into a trilemma, which, with my pointer, which is the materials into this equation. Because we believe that biomass can have a non-energy function in the long term, which can in turn leads to building blocks, building materials for edifications, for infrastructure, for plastics, and that can lead to, including for net negative emissions because it stores carbon. So we believe that deployment of biomass, not only for energy and for food, but also for materials, can have a contribution factor for climate change mitigation. And we asked in this presentation, what is the role of biomass in this competition between energy, food, and chemicals? It's worth mentioning that this presentation is based on the three following scientific papers. I can add the link later in the chat. First, we have improved biomass to chemicals representation in the BLUES model, which is the Brazilian integrated assessment model. On the left-hand side, you can see the ancillary technologies, which we have updated, improved representation in terms of biomass conversion towards liquid fuels such as naphtha, diesel, jet fuel, heavy oil, gasoline, and from various sources of biomass, including gasification, pyrolysis, chemical conversion, and dehydration of ethanol and oligomerization of ethylene into a larger chain of hydrocarbons. On the right-hand side, you can see the main technologies that we have upgraded and uploaded into our integrated assessment model, mostly for the production of plastics, which is a major chemical component of production in Brazil. So ethylene, propylene, butadiene, and BTX. Sorry for those who are not chemical engineers, a bit of chemistry there. Basically, what I'm trying to show is that we have routes that are fossil-based routes, mostly from natural gas and oil. We have bio-based routes, a few of them from synthetic liquids, from pyrolysis oil, from oil crops, from ethanol. And we have some options that are fossil and bio-based, depending on the source of the component. Such, for instance, the processing naphtha that comes from biomass or oil. There is a bit of an advertisement here. There is a more in-depth analysis of chemical routes that we have added into our global model that will happen tomorrow on Sectoral 2 session. For this study, we have performed 3 scenarios with some sensitivity analysis. We have a business as usual module scenario with the biomaterials mode on. I'll try to explain what that is. We have a well below 2 degrees, which is consistent with the well below 2 degree scenarios for Brazil. And we have a demand reduction scenario in the 1.5 below 2 degree scenarios, which is based on the lower demand for single-use plastics and changes in demand. As for sensitivity analysis related to the reference case, we did a higher oil price scenario just to see the impacts of trade and the technologies for supplying liquid fuels in the baseline. Related to the well below 2 degrees, we had a scenario where we switched off the options for biomaterials and saw the impacts on the use of biomass, land use change, emissions, and so on. And on the demand reduction scenario, since the demand for plastics was reduced, we proposed the substitution of carbon-intensive materials by plastics in order to gain a little bit more of a market share. And we proposed 2 scenarios: the substitution of cement by plastics in infrastructure and the substitution of steel by plastics in infrastructure, in long-term, long lifetime materials. We have several disposal options for plastics, landfills, incineration, recycling, long lifetime materials, and the coefficients for emissions and the energy inputs are all based on this paper, which is the second paper on our list, that focus on the life cycle analysis of fossil and bio-based plastics on all final disposal options. Going a little bit into the results, we have here the results for the baseline or business as usual scenarios in the well below 2 degrees. The third thing that we see in the baseline scenario is that there is a cap, there is a peak of biofuels in our scenario because of electrification of the fleets in the baseline scenario and efficiency improvements in the transportation sector. Ethanol and biodiesel reaches a cap, a peak of production in 2030, seeing that it reduces production of biofuels in the baseline. In the well below 2 degrees, there is a huge increase in bioenergy production, mostly advanced biofuels, but also a little bit of an increase in ethanol with CFs, ethanol with carbon capture from the fermentation process of the ethanol production plants that leads to a new drive for production of ethanol, increasing the production in the well below 2 degrees. Related to land use, the baseline scenario of business as usual scenario mostly shows an increase, land use change towards degraded pasture in order to improve production for cattle, for ranching and meat and milk. In the well below 2 degree scenarios, we have a more shifted version of a more disputed land use change, mostly focusing on carbon negative emissions such as recovered pastures, afforestation, integrated systems, which will be the focus of another advertisement here, another detailed presentation on our land use change model on Land 2 session tomorrow, if I'm not mistaken. Related to the bio-based petrochemical production, we can see here that on the baseline, there is already a production of bio-based chemicals. This is related to an installed plant in Brazil that converts ethanol to ethylene. And in the well below 2 degrees, we can reach up to 33% of plastics made from biomass. Some of these plastics are made from ethanol, such as ethylene and butadiene. But some of this is also made by steam cracking the bio-naphtha, the naphtha made by advanced technologies for biomass conversion. This is a more in-depth analysis of what is the share of routes per type of petrochemicals. I'm not going into details, but just showing here ethylene production and butadiene production by ethanol is quite reaches 20% of the market, and some of this naphtha steam cracking is bio-naphtha, it's not fossil naphtha. One side effect that this scenario has is the reduced refining through output, or the utilization factor of the refineries in Brazil, mostly in the southeast and south region of Brazil. Not going into detail here. There is a presentation. When I finish this presentation, the next room, if you are able to see it, there's a presentation about opportunities for co-processing biosources in refineries in Brazil, also related to this huge drop in refinery through output. On the sensitivity analysis side, the higher oil price scenario on the reference case led to more exports of oil in Brazil, less imports of jet fuel and naphtha in Brazil, which is really significant in Brazil. And what I like to focus on the right-hand side is where we turn off the biomaterials. There was an interesting result that showed that the competition happened not on land use, on food production. It had no impact on food prices, on land use change, but it did change where the biorefined product would end up. It basically switched from a non-energy use, for a stream cracker, naphtha, for instance, to an energy use. It ended up going to the gasoline pool, and we imported more fossil naphtha for non-energy purposes. The second is that there are investments for advanced biomass to liquids technologies for hard-to-abate sectors, which, again, there are some other presentations from our group on this year on the conference. On the sensitivity analysis side, mostly we show that There is a trade-off between emissions from the chemical side and industrial process emissions from cement and steel, which can lead to an optimal result, which can lead to a little bit more room for the electricity sector, the power sector, the transportation sector to emit. And there is a trade-off between a shift in the final disposal of plastics. Finally, without spending too much time on the conclusions, we can discuss this a bit further. Is our belief that without addressing materials in integrated assessment models, there is no rapid full transitions because fossil fuels are required for non-energy purposes. That means that the biomass trilemma, how we're calling it, for food, energy, and materials is significantly important and affects the oil sector and petroleum refinery sector. And we show that Brazil, up to 2050, can have almost a third of its petrochemical production coming from bio-based sources. I believe these are my main conclusions, and I will end here. Thank you very much.
Well, thank you very much. Very interesting. I have a couple of questions, but probably let's leave it to the end. Meanwhile, one more time, I encourage you to put the questions into the chat so that we will have a discussion at the end. Now let's turn to our final presentation, Jay FUHRMAN. And I hope, Jay, you are here and you can start sharing your screen. And so we are going, I'm hoping to hear about the direct air capture, and Jay FUHRMAN is from PNNL. So Jay, the floor is yours.
Great, so thank you for the kind introduction, and thank you for taking some time to listen to my talk on some work that my colleagues and I did while I was a PhD student at UVA in developing SSP-consistent direct air capture scenarios in 1.5 and 2 degree futures. And I'm pleased to share that this study was recently published in the journal Environmental Research Letters. So the motivation for all of this work, as has been discussed by the other presenters, is that to meet these deep mitigation goals, consistent with limiting warming to 1.5 or 2 degrees C, we're going to need CDR for below 2 degree target, and especially below 1.5 degree target. And so, and the longer we wait to really start mitigating deeply, the more we're going to need to rely on these to kind of come back and remove the CO2 that we're continuing to emit. So the question is, where will these negative emissions come from, and how will they kind of interact? How might they interact with food, energy, and water systems? And in particular, for us, what role can emerging technologies like DAC that are only fairly recently beginning to emerge in the IAM literature play in contributing to the negative emissions and also limiting some of the perhaps negative trade-offs? So we used GCAM, which is the Global Change Analysis Model, and it has detailed treatment of the energy, land, water, and climate. And we sought to add a representation of direct air capture technology. So we looked at 3 different main archetypes of DAC. The first is, if I can, the first is this high temperature DAC process that relies on natural gas for process heat. The second is another high temperature DAC process that uses that is fully electrified and uses solely electricity to do the solvent regeneration. And then the third is a low temperature DAC process that uses a heat pump to regenerate the sorbent. And so the way that we kind of set up the competition was we had kind of a fourth rather dummy technology that basically just is free and doesn't really do anything. And then the 3 DAC technologies that we have represented here kind of compete against each other as well as doing nothing. And so therefore indirectly against, other negative emissions, as well as mitigating. So basically avoiding emitting CO2 altogether. So in the context of the SSPs, DAC, to our knowledge, hasn't really been looked at in the context of the SSPs, but it poses some unique interactions with the socioeconomics and policy factors, because unlike BECCS, it consumes rather than, in theory, produces energy. And so just to briefly go over the SSPs, SSP1 is a scenario, sustainable development, where you have relatively lower per capita energy demand and lower cost for renewables, and basically generally easier to mitigate, as well as easier to adapt to the impacts of climate change. And then in contrast, kind of on the other end of the spectrum, we have SSP3, which is a rocky road scenario where it's very difficult to mitigate and adapt. And then SSP5 is a fossil fuel development scenario where there's higher per capita energy use, generally a little bit more expensive on the renewables, and so fossil fuels continue to basically dominate the energy system, however CCS is available. And then SSP4 is a scenario of deepening inequality, where in particular land use, carbon pricing for land is very challenging. And then SSP2 is kind of the middle of the road scenario, where you have, it's kind of a mix of the other four. And so for each of these SSPs, we kind of did a little bit of a meta-analysis for costing out and parameterizing the electricity, natural gas, if any, as well as non-energy cost inputs of DAC, and as well as its improvement or potential improvement over time. So here we assume by 2050. And so you can see that in the intermediate assumptions, both the energy and costs generally improve. And then in SSP3 for DAC, we have where basically it remains high cost and relatively high energy per unit of carbon captured. And so so for SSP1 and SSP2 we kind of assumed the intermediate improvements in the technology. SSP3 again we assumed much more pessimistic on it. And then SSP4 and SSP5 were ones of advanced technology, where both the cost and energy inputs improve considerably. So walking through the results for this figure shows for each of the scenarios that we ran. We ran our parameterizations of DAC along with the kind of background parameterizations for all of or assumptions rather, for all of the different SSPs. And here this chart shows positive and negative CO2 emissions. A couple notable results here. In SSP1, DAC does reach multiple gigaton scale, but its contribution is much, much lower than in the other scenarios. And this is for a couple of reasons. One is just basically it's much, much easier to mitigate in SSP1, as well as use land to soak up carbon. We also tightened, GChem has a GDP constraint that you can apply to all forms of negative emissions. And so here DAC is included under that constraint. So by default, this is 1% of global GDP is kind of the amount of that can be devoted to financial transfers for negative emissions. So basically paying for it. So we tightened this by a factor of 2 in SSP1, and this was explicitly done to kind of envision a perhaps more sustainable role, a less prominent role for DAC. Whereas in the other SSPs, the constraint is higher, and you can see that in SSP4 and SSP5 in particular, we see tens of gigaton scale deployment. So this next chart is showing results for geologic carbon storage. And here you can see the different archetypes of DAC kind of disaggregated in the different shades of purple. So this is basically carbon that's either being captured from industrial sources or bio-CCS and DAC and going into the geologic storage. So all of our scenarios project tens of gigatons of CCS by the end of the century. And interestingly, DAC and BECCS appear to dominate the CCS. And so the majority of the CCS in these scenarios is coming from negative emissions, as opposed to just emissions abatement where you're capturing at the point source smokestack. So next for primary energy, this was a very interest to us because DAC does have this direct energy input requirement, but it also has an indirect effect wherein it allows higher energy consumption, basically because it allows higher energy consumption due to lower CO2 prices. So the energy impacts are substantial, but relative to the other things that we are projected to need energy for, be consuming energy. For an SSP1, its contribution or consumption for primary energy is fairly low, but in SSP4 and 5, it does get up to about between 15 and 25% of present day global gas demand by the end of the century, which is just truly, truly enormous amount of energy. And so in those scenarios in particular, we would need a huge, huge amount of natural gas. Another thing that I'll just note here for clarity is that the electricity for DAC, it's not broken out separately here, but it's included in the mix of the other primary energy because electricity is secondary energy. So then DAC for water consumption, the high temperature DAC process does require process water for the aqueous solvents rather. It has a fairly large dedicated water requirement, but it actually does reduce irrigation for bioenergy crops. And so in doing this, it can actually reduce the amount of water that's required for CDR globally. And by kind of decoupling, you can kind of put it wherever you want. And so you could, in theory, choose places that might have less competition for water from agriculture. And then on land use change, we didn't really consider the direct land use change of DAC. We did some back of the envelope calculations and found it to be much less than 1% of global land area. However, DAC does have some indirect effects in terms of particularly the amount of biomass cropland area that you have. And so it is able to reduce that by between 18 and 31%. But, as you can see here, in meeting these deep mitigation scenarios, so below 2 degree and 1.5 degree, it's truly massive, like millions of tons of land use change, particularly for bioenergy and forest that just would need to be dedicated to pulling carbon out of the air. So to kind of conclude here, the future socioeconomic and policy developments, particularly whether or not we start down this deep mitigation pathway in either now or in the immediate future, are going to heavily influence the requirement for and the balance of negative emissions deployment, including DAC. So DAC does allow delayed mitigation in most of the scenarios that we ran, but if we kind of delay at the risk and then fail to scale it up at these massive scales and visions, we risk basically permanently overshooting our climate targets, which is consistent with the findings of other literature. So the sustainable development scenario in SSP1, we tried to explicitly limit the reliance on the future negative emission deployment by and kind of envision basically a sustainable role for DAC and other CDR large geologic carbon storage requirements, so 10 plus gigatons a year in all of our scenarios. And our hope is that the parameterizations that were developed here and kind of the scenario design, we hope that it might help other IAM teams inform them as they seek to try to model DAC as well. And so just briefly moving on to some work that we have in progress. So we have now in GChem on the left of the slide here, treatment of DAC. And so our hope is to add other more of a breadth approach of negative emissions options, including direct ocean capture, as well as accelerated weathering and soil carbon with biochar or no-till agriculture. And so the idea would be to eventually be able to look at, all of these kind of and see how they interact with one another. And these 6 technologies are kind of singled out for analysis in the US Congress. There's a report on CDR, and so these are the kind of 6 technologies that they're most interested in. So I think that's my time. And so I just like to take a moment to acknowledge my collaborators and co-authors on this paper, as well as the U.S. Department of Energy's Fossil Energy and Carbon Management Office, as well as the UVA Environmental Resilience Institute for supporting this research. And if there's time, I'd be happy to take any questions you may have.
Well, thank you very much. Yeah, very interesting. Really looking forward to a discussion period. We have 15 minutes currently set up, and we still have that 15 minutes. So thank you for all speakers of staying on time. So there are a couple of the questions in the chat, both to, well, I see Pedro, and there is a exchange on the presentation of Thailand. And I see Volker, I think you have a question to Jay. So maybe let's start with that. So maybe let's make it a little bit more personal. So Volker, let's start with you. If you can unmute yourself and ask the question.
Yeah, sure. Thanks for the opportunity, Sergey, and thanks, Jay, for the very interesting talk. You were highlighting one of the benefits of DAC being the possibility to delay mitigation action. I mean, assuming that upscaling can really happen. I mean, one of the issues related to the delay is that you end up overshooting your temperature targets, right? So it doesn't come really, I mean, it's not really equivalent in terms of the goals that you are meeting and climate and also impacts, if you think of whatever stress on ecosystems to adapt to interim higher climate change. So how did you evaluate that, if at all, in your assessment?
Yeah, Jay, go ahead. If you have a response, or you can just say, oh, it's a matter of future research, whatever preference.
Yeah, so I guess the short answer is that GChem doesn't currently have the capability to look at kind of the I guess, is your question about damage functions? And so that isn't really something that we considered. There's some pretty cutting edge research that's been published in the last couple of years that's like trying to that's doing that with, like, in terms of agricultural yield loss and like the economic impacts of that. And so, but I guess the short answer to your question is that we didn't really like explicitly evaluate the the overshoot cost in our objective function, I guess.
So if I can just clarify with a follow-up question. So you basically look at a temperature goal at a given point in time, whatever, end of century or something, and all scenarios basically meet that? Is that the setup?
Yeah. So yeah, we use kind of the SSP RCP framework, and so all of them kind of target whatever level of radiative forcing by the end by 2100, and then it kind of determines a CO2 price path to meet that, and exponentially increasing CO2 price path to try and meet that.
Thank you. Okay, so now let's try to switch gears. I see a lot of exchange between Nico and Achiraya. So I'm not sure if you already have asked all the questions and got all the answer, but Nico, if you want to follow up, you can unmute yourself and let's see.
Thanks, Gay. I think Achiraya has answered my questions. Thank you for that, by the way. Thanks.
Thank you. Okay, good. Nice to hear that. So we have another question on direct air capture. Yang Yu, do you want to unmute yourself and ask the question in person?
Yeah, sure. So Jay, thank you very much for the talk. So I think I have two questions. The first question is that you mentioned about the DAC improvement in one of your slides. I'm wondering whether that improvement is based on some technology learning approach, also as well as the DAC deployment output from the games, from the GChem model. And the second question is, I think some of the result you have shown, for example, the water depletion is really depend on the capacity of different DAC heat combination that you mentioned in your study. So I'm wondering whether how does those different combination of DAC and heat and their capacity change over time? Is there a specific option that will stand out over time?
Sorry, I'm just looking at the chat real quick. So to answer your question about the kind of parameterizations, they were exogenous, and so GChem doesn't do like endogenous, like, technological learning. We also, I'll just add that we were pretty conservative with, how we parameterize it, and we based it, we kind of assumed like kind of current literature is like the floor for like how cheap and energy efficient it could get. We just wanted to be very conservative in the way that we modeled the technology, given its potential in, a model like GChem to kind of take over. So I'm not sure if that answered your question. And then on the water side, could you just restate your question on the water?
Yeah, so I think my main question is, I think for some of the result, especially for the water consumption, it's really depend on the which kind of DAC heat combination you have been used. For example, if you use more solvent DAC, then you have high water consumption. So I'm just wondering how does different DAC heat option and the capacity, how does the capacity change over time in the model?
So we, to our understanding, the high temperature DAC is the one that, the solvent based one is the one that uses a lot of water, whereas the sorbent based is lower. Because the high temperature DAC, the natural gas process in particular is kind of seems to be the most mature, it does end up kind of mostly dominating. You can see it in the CCS. This dark purple is the natural gas fired process, and then the low temperature process is the lighter purple. So the high temperature does kind of dominate, but then we also have, it's not shown directly here, but the indirect water consumption associated with electricity that goes into DAC is kind of included in this estimate here. And we don't show them in this presentation, but in the SI of our paper, we do have no DAC scenarios. So scenarios where DAC is basically just not available. And so you can kind of compare the water consumption between them and get an idea of like what the marginal impact is.
Okay, great. Yeah, thank you.
Thank you. I see another question to Jay, but before we do that, Pedro, if I may ask you a question, and maybe you already answered that in the chat or in the presentation, but if yes, so please repeat. So usually the question, whenever you're talking about bioenergy, right? So the question is, okay, what about food impact on food prices? So how that is going to affect that? So can you elaborate a little bit in terms of your findings? Is it a big impact, no impact, or what's the story? Or you didn't take that into account in your study, or?
Yes, we have assessed that in this particular study. What happened was that the land use change. We in our national model, we are able to supply a large portion, almost I don't remember by heart, but maybe like 7 exajoules per year of advanced biofuels, and still have a lower impact on land use change in food than in the baseline scenario, because deforestation in Brazil is a major impact on land use change. And when we drive, the model shifts towards a 1.22 degree scenario, it basically is able to keep up with demand, have a lower impact on food prices. It doesn't have a big impact. In fact, we have agricultural practices that are more efficient actually during the 1.5, because they are less extensive in land and have a higher quality of meat, a higher yield towards meat, for instance, in milk. And overall, when we assess all the scenarios, we have a marginal effect on prices. I believe I mentioned in the slide and in the comment, when turning on and off the biomaterials mode, there was less than 0.2% changes in the average average food price of food baskets. Land use change remained barely unchanged, except for a few minor changes in net options, in net negative emission options, such as recovery of pastures and agroforestries and integrated systems for production of food, energy, and livestock. So there are impacts on land use change, but mostly you can see that they are really neglectable, and they don't have an overall high impact on food prices and food demand, and we can even achieve net negative emissions in land use change.
Thank you. Interesting. Okay. So we have another question to Jay. So David McCollum. So Dave, can you unmute yourself and ask a question?
Yeah, thanks a lot, Sergey. Yeah, thanks, Jay. Great presentation. It was the only one I caught in this session. Sorry. I missed Pedro's and others. But Jay, question on yours on the regional aspect. I didn't see any figures on that in your presentation. Maybe it's in the paper, but are there any interesting stories, noteworthy insights, kind of when you drill down to the regional level? Or is it just as simple as, well, there are parts of the world like South Asia that just have less bioenergy potential, therefore they gravitate to DAC instead of BECCS? Or is there something more complicated and interesting there from a systems point of view, because they have more solar, wind, abundant natural gas in North America, anything that came to mind, I think I'd be interested to hear.
Yeah, sure. So in this particular study, we didn't really focus as much on like the regional impacts. However, we in another recent study that we got published in Nature Climate Change, we did kind of look at regionally where DAC might be deployed, and like you said, it was generally kind of dominated by places like the U.S. and China that have both abundant geologic storage capacity as well as natural gas. And then for the electricity piece, the ability to, more abundant or cheaper renewables. So that I can post a link to that paper in the chat if you're interested.
Thanks a lot.
Yeah, thank you. Did I get, so Jay, again, well, I guess you're the last one, so we remember your presentation more. So my apologies to other speakers. But Jay, if I got the cost numbers correctly from your slide, it looks like you are going to like $50 in terms of non-energy costs, right? $50 per ton of CO2. So, well, I'm less familiar with non-energy costs. So if you like tell me, oh, what is the full cost of these three options in terms of dollars per ton of CO2 in your optimistic case? So what are they? Can you tell me from the top?
Yeah, so I don't have them in this particular presentation, but the non-energy cost is kind of the levelized capital plus labor plus anything.
Right, but well, my real question. So usually people are saying, oh, well, direct air capture can be as low as $100 per ton of CO2. Well, and I know a lot of people who would say, well, that's a dreamland. So I'm just trying to compare your $50. Is it like $100, or your $50 is $75, or your $50 is $500? So what ranges we are talking about the total cost of direct air capture?
Yeah, sure. So I think I don't have those results offhand, but I think that if you, in the optimistic case, it ends up being on the order of like 300 to 350 total cost, current dollars. I'd have to double check that though.
Okay, no. I'm just trying to gauge like how optimistic you are. And well, we all know that if you make heroic assumptions, you will see a lot of technology coming out. I'm just trying to understand where. Okay, so I think we have 30 seconds remaining. Any last questions or any last words from anybody who wants to raise? I'm looking at the chat. I don't see any, or anybody wants to say. Well, again, thank you very much. I think it's a very good session. Again, my apologies that I've missed the beginning of the session, but I think we have a very good discussion. And well, again, use this opportunity to interact with others. We have many chat rooms, especially for that purposes. And one more time, thank you for your presentations, and have a wonderful rest of the conference. Thank you. Have a nice one.